Hi, I'm Dan Quiggle with DQDesign, and after 30 plus years of mechanical design, I put together a list of my top 10 steps of the mechanical design process. When I was little, I was always making something and tearing apart my toys, rebuilding them with different purposes. I had an erector set, tinker toys, and built all kinds of Rube Goldberg machines. My father was a machinist, and my brother was into motorcycles and drag racing. Our house was a neighborhood shop for motorsports enthusiasts, which I learned tremendously from. I started working at a motorcycle shop when I was 15, installing exhaust systems and jet kits, changing tires and oil. I bought over 200 used motorcycles and fixed them up and sold them. While going to drafting and design school, I was hired by a small local engineering firm for drafting on Disney ride projects in Orlando. When I was 18, I started my own drafting business and would sell computers, AutoCAD, and training to local architectural firms. At 19, I started working for a drafting service and began hiring and managing drafters for various companies and projects. At 21, I started working for a retired gentleman that ran Pratt & Whitney's propulsion test development program in South Florida and started his own consulting firm. I was exposed to all kinds of interesting propulsion test applications, facilities, equipment, and industrial facility projects. We grew the company from the two of us to over 80 people as I took over management when he permanently retired. All along the years, I've been involved in a big variety of projects in and outside of propulsion testing that included all major engineering disciplines, exposed to all kinds of people, industries, physics, applications, tools, techniques, methodology, and watched it all evolve tremendously. I mentored a FIRST Robotics high school team for 13 years. We exposed kids to solving complex engineering challenges rapidly with industrial process solutions, which included mechanical, electrical, software, fabrication, and implementation of constant revision and debugging. Every year we improved to make it regularly to the top of the world championships. Proper mechanical design is truly an art. I've always had a passion for mechanical design, and I love finding simple, elegant, effective solutions to complex problems. I believe it's more of a talent than a skill. Although most aspects can be taught, there's some things that just can't. Mechanical design is an iterative process, and because time is a costly factor, arriving at an optimum solution as quickly as possible is at a premium. The outcomes are non-deterministic, and the results are weighed on many factors, so talent and experience in the beginning of any project makes all the difference. Characteristics of a good designer would include the ability to visualize the three-dimensional aspects and physics of the concept in operation, being able to freely consider all possibilities without getting hung up early on an idea, and can convey ideas effectively, especially sketching, as CAD can be cumbersome in the beginning. They're open to feedback and being a part of a team iterative process. Of course, relative experience in this process adds important value, and training can only go so far. Engineering emphasizes analytical skills and not necessarily design applications. Thus, the distinction should be noted between designers and engineers. A designer with analytical skills is a great combination. Add administrative and people management skills and you have a great project manager. I do not profess excellence in all categories, but I'm somewhere in the middle of the mix. And so with that introduction, here's my top 10 steps of the mechanical design process. Step 1. Industry comparisons. The first thing everyone does with a problem is Google it, and Google usually gives you an abundance of information that will help for the most part. Commercial off-the-shelf solutions are step 1, and the good news is that most industrial products have drawings and CAD models available for download. Reaching out to companies in similar industries is also an option if they're not a competitor. Keep in mind that a lot of solutions are out there, but they're under non-disclosure for whatever reason and not available to the public. When you're in the innovative phase and reaching out to companies for information, sometimes you'll find they're apprehensive or unwilling to help and that they do not want to innovate for free. They may not necessarily be in the business of your specific needs. Effective initial research is the key to success, and the outcomes can vary dramatically when it comes to custom design engineering solutions. So if you didn't find it fit or you're just confused, then a custom solution may be in order. Step 2. Requirements and preferences. Depending on the scale of your endeavor, defining requirements can mean many things. So getting all the stakeholders involved early and bringing the best information to bear is extremely valuable. Overly conservative estimates on loads can add substantial cost and complexity, so be mindful of real data. Budgets and schedules usually drive the rest of the process, and having the right resources available will dictate the former. With large-scale projects, I always recommend an initial study, thus structuring the contract into 3 phases: the study phase, design phase, and then the fabrication, assembly, and installation phase. A study will consist of general requirements gathering, conceptual design, trade study, a review, market research for products, and then the fabrication, assembly, installation, and then an estimated budget and schedule is put together, which includes the design phase. And depending on the best path forward with your design, your requirements will likely change. You don't want to be stuck with a budget and schedule that doesn't match your optimum design options. Studies result in substantial requirement definition. However, most customers are looking for an all-inclusive proposal, and this presents a lot of risk for the design firm, where a study phase should eliminate the majority of questions and provide a quality schedule and budget for the design and fabrication, assembly, installation phases. Usually studies are a small fraction of the project budget and provide invaluable insight. Of course, finding the right resource for the study is critical, so doing research on experienced design engineering firms is where to begin. Step 3, cost effectiveness. Design, engineering, drafting, materials, aesthetics, manufacturing, shipping, assembly, installation, training, commissioning, safety, insurance, maintenance, life cycle, they all play a role in the decision-making process. As part of the requirements phase, obviously cost pushes the margins of possibilities from a yes or a no to bells and whistles, and you get what you pay for. The vast majority of design engineers are willing to refine their designs indefinitely if you let them. With budget and schedule in mind, knowing when to sign off on a design can be tricky, depending on the level of risk remaining. So good communication between finance and design needs to be established and consistently maintained. An optimum design can be embellished if upgrades and preferences are desired, but the simple solution should always be the foundation wherever possible. And step 4, following the loads. The primary consideration of a mechanical design is the function, and thus the loads and their operational load path are the primary consideration of its size, shape, and materials. FEA is a wonderful tool to identify stresses and put the emphasis of design where it needs to be. When simply done harmoniously with form and fit, it's a beautiful thing. And this is what we should all strive for. Many times the conservative approach is to throw superfluous material at the problem, which can be costly, ugly, and unnecessary. It can also add complexity and weight. If the load path isn't obvious or intuitive, a free body diagram can help lay it out. Obviously, when form and fit are the design emphasis, you do what you can. Step 5, functionality. All designs have their limitations, but prioritizing functionality over any other conflicting factor is logical. If form or fit have a priority, you should try to optimize functionality however possible. Get feedback from operators of similar systems. Building physical models to run through process sequences can be invaluable for more complex systems. 3D printers are great for this. Analytical simulation is a fantastic tool for discovery and development of complex systems. Where people are interfacing designs, safety is critical. Research OSHA guidelines and mitigate any possible risk. Integrating tooling into the design or making interfacing features congruent throughout the system is important. Make interfacing features accessible, simple, and intuitive. Replacement of wearable components should be integrated. Step 6, simplicity. We're always seeking the path of least resistance and to minimize impact on each design factor. Going through these steps of the design process, you'll see my theme is all about finding the simplest solution to each factor. Each step will contribute to an optimized design. And that's not to say if you find yourself cornered by complexity, there's an easy way out. I always find value in roundtable discussions. We sometimes have challenges and give everyone a shot at the problem. Brainstorming as a team invokes a lot of dormant ideas that we can't realize when we're stuck in a loop of traditional thought. So be open-minded for as long as you can until the budget and schedule say otherwise. Designing in a vacuum is strongly discouraged. Use the least amount of material wherever possible and iterate where the complexities remain. And step 7, materials and their environment and usage. I live near the ocean and salt corrosion is always an issue, as many of the designs I've done tend to live outside in the salty air. Extreme conditions such as cold, heat, water, sand, wind, sun, handling, etc. could dictate a scientific approach to material selection. Materials play a big role in the cost, strength, weight, durability, manufacturing, aesthetics, and just general quality perception. Generally speaking, I design for the lowest cost unless it becomes marginal in whether usage or aesthetics play a role. There are always new products and methods on the market, and whatever your product will be exposed to, it's good to get an update on what's available from suppliers in that field. They're always happy to review your design for product and material line opportunities. However, as you enter into competitive design, an expert may be needed. Consider renewable material sourcing and the environmental impact of your materials. Step 8, aesthetics. Quality look is always important, and safety also plays a role in aesthetics. Considering workability such as handling features is very important. Integrating a theme or proper coatings and material treatments can have functional purposes as well. Be mindful that some designs may become a primary tool for someone for years to come. If it's ugly or unprofessional looking, it can leave a bad impression. Step 9, manufacturability. Seek manufacturing, assembly, and installation feedback early and often, but don't waste their time. Get your best concepts together with good drawings, dimensions, sketches, materials, etc. And when they're giving you good advice on materials, tooling, methodology, it can be invaluable. It could be possible that they're trying to push you to adapt the design towards their tooling or skill set, so you should seek a few opinions and choose what you think works best for you. Good partners in fabrication, assembly, and installation will make all the difference in successful execution, especially if they point out errors in your design rather than running with what you gave them and finding out later things need to be redesigned after they were made. And step 10, installation sequencing. Plan out the process from vendors, source materials, fabrication, assembly, installation, maintenance, etc. You may find that structure won't fit on a flatbed or under a bridge. It may exceed highway transport loads. Will the wind blow it over during construction? Does anyone in that town have a crane or tool needed on Friday? Does a standard socket extension reach that nut at the bottom of that pipe? How will they fit that ring retainer on that side of the pin? What if the part in the middle breaks? How will they replace it? Everything looks great all together in your model, but how it gets like that is another story. Modular sequenced assembly and installation procedure drawings will expose issues like these, and rather than stopping at a bubbled material list assembly drawing, installation drawings are invaluable on basic or complex assemblies, and then walking through your designs with any takers will provide everyone with confirmation you did a good job. This is just a high-level list. Many of these aspects have been expounded on in industry standards that vary depending on the product. I apply all of this logic as I go, and much of it in this sequence. However, it all acts in a feedback loop where steps get repeated in iteration. If you have any questions or comments, please let me know. And of course, if you'd like assistance in your project, that's what I'm here for. I partner with excellent design engineers for various disciplines, and together we make a great team. This is my passion, and I get excited about new challenges, so I'd love to help. Thank you for watching my video. If it helped, please click the like button and subscribe to my channel.